Last lesson we differentiated single terms to the power of n, where n was positive. Today we'll look at situations where it's negative. It's not much different, but there is some understanding involved. Have you worked out yet that when you derive a cubic, you get a quadratic? For instance, if you've got f of x equals x cubed, f dash x will equal 3x squared by rule. So because the highest power will get reduced by 1, what we'll get is from a cubic we get a quadratic function. From a quadratic we'd get a linear function. From a linear function we get a constant function. Okay, so here's a challenge. Consider the following hyperbola. What will the gradient graph of a hyperbola look like? So if this is y equals 1 on x, what will dy dx look like? Okay, well, let's have a look at this. There's a negative gradient all the way along this line here. Okay, the gradient is negative all the way along here because as x increases, y decreases. Now, along this line as well, we've got a negative gradient all the way along this line. And in fact, the gradient along this line here would be, so the gradient here and the gradient here would be exactly the same value. Okay, the gradient here and the gradient here will be exactly the same value. Okay, the tangent and the tangent gradients will be equal. So what's it going to look like? Well, it's going to be negative, okay, because we've got a negative gradient. Now, what's the gradient here? All right, well, it's extremely negative. I know that's not really great mathematical lingo, but all I can say there is it's extremely negative, right? And what happens to the gradient? Very negative, very negative, very negative, getting lower though, getting lower, getting lower. So got a gradient of about 1 there, okay? So it looks like it goes along a 45-degree angle, okay, or rather -1. And then getting still negative, but getting lower, 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 and it sort of flattens out to be almost 0, okay? So what I'm going to do is say that this is going to be very negative, so an extremely negative, getting lower, and approaching 0. So we've got that particular situation for the gradient graph there. Now over this side, it's exactly the same story, right? Over here, we've got an almost 0 gradient and a very negative gradient, and it must be symmetrical as well, right? And notice what that is. That looks like a inverted truncus. So if you recall, a truncus graph looks like that. Probably the worst truncus graph ever. The Cartesian plane first. So that's the standard truncus, y equals 1 on x squared, and all that the gradient graph will be is an inverted truncus. Okay, so what I'm expecting f dash x to be is a -1 on x squared, with that value maybe being a, I don't know whether there's a dilation or anything like that, but I'm expecting it to be an inverted truncus of some sort. That's what I expect. Right, so what we're going to do is get the derivative of y equals 1 on x by first principles. So let's let f of x equal y equals 1 on x. So we can operate on f of x. All right, so let's first of all note that to get the derivative via first principles, what we're going to do is say f dash x is going to equal the limit as h approaches 0 of a point which is x plus h, take away another point x over h, right? So this is taking a point extremely close, evaluating the y values, and we've already assumed that we've subtracted the x values to get h. All right, let's go for it. The lim as h approaches 0, don't forget that. All right, so we're going to go 1 over, so I'm going to jam in x plus h into f of x. I'm going to do f of x plus h, which gives me 1 over x plus h. Take away 1 over x all over h. Alrighty. Lim as h approaches 0. Now what I'm going to do is try to get rid of this h at the bottom here. And to do that, I'm going to find a common denominator and combine the numerators. So I'm going to go x plus h, take away 1, no, x plus h over x plus h. Now what the hell have I done there? I've multiplied by x over x, and I've multiplied by x plus h over x plus h. All right, and that's given us this scenario here. Remember, we're still over h itself. Okay, so this is going to be the limit as h approaches 0, x take away x plus h over x plus h. Now, what would happen here is it's being divided by h. All right, limit as h approaches 0. Now, this is going to be x take x, which will cancel out, and we would be also subtracting h. So we're left with subtract h on the numerator. Now, divide by h is the same as multiplying by 1 on h. So I'm going to do that and rewrite this as xh, x plus h. All right, those h's cancel out, leaving me with -1 over x squared plus xh. All right, ready to apply our limit. So we'll limit h and let it approach 0, which means that this term is left unaffected, 1 over x squared. This one here, h approaches 0, 0 multiplied by x is x. So we can assume that f dash x is equal to -1 on x squared, which seems to be suggesting, as we felt with the diagram, that the derivative of a hyperbola is an inverted truncus. So what we do, girls, is we essentially use the same rule as 17b to get derivatives of functions with negative powers. Okay, so if I wanted to do this without first principles, if f of x is equal to 1 on x, I rewrite f of x as x to the -1, and I simply use that same rule that I used prior, which is -1 multiplies by the coefficient, which is -1, x to the -2, which written with a positive index is -1 over x squared. Gee, isn't that a hell of a lot easier than doing all of this? All right, so the rest of these we're going to derive by rule. So find the derivative of this where x is not equal to 0. Now, why can't it be equal to 0? Because that's the same as 2 over x cubed. And if x is allowed to be 0, then we get a divide by 0 error there. So I'm going to say let f of x equal x to the 4 take away 2, x to the -3 plus x to the -1 plus 2. That's just so that I can use function notation because I really like function notation. So 4x to the 3 is that term. -3 multiplied by -2 is 6. X to the -4. -1 multiplied by +1 is -1. X to the -2. The constant chops out because that's x to the 0. 0 multiplied by 2 is 0. All right, so probably the last thing to do on this one, and you don't have to do this unless it's really stated, but 1 over x squared is write your terms with a positive power. All right, so find the gradient of the tangent to the curve determined by the function that at the point 1, 2. All right, so what this is, it'll be, I don't even know what that graph looks like. Let's graph it. Where's GeoGebra? All right, so f of x equals x squared. So it's a parabola with a truncus added to it and a hyperbola added to it. All right, so there is my function, rather weird looking function there. And what they want us to get is the gradient of the tangent at the point 1, 2. So basically we want a tangent there, so we can see that the gradient of this tangent is going to be positive. Okay, I can even get a rough estimate of it, like as x. I don't think it's almost going to be 1. M equals 1. That's my guess. Anyway, let's find out what calculus tells us. Okay, so the first thing I'm going to do is write f of x with negative indices, x squared plus x to the -1, because that's going to allow me to use my derivative by rule more effectively. F dash x equals 2x, take x to the negative 2, f dash x equals 2x, take away 1 over x squared. All right, now what we want to do is find out its gradient, or the gradient of the tangent at this point here. So who or which function are we going to ask? Well, the original function, remember, gives us y values, and we're not interested in y values. In fact, we know what the y value is going to be. It's going to be 2. What we want to ask is the derivative function. So I'm going to slam x equals 1 into the derivative function, and basically I'm saying to the derivative function, hey, can you please tell me what your gradient is at x equals 1? Can you please do that for me? So this is what I'm asking, f dash 1 equals. I'm saying, please tell me what your gradient is, or what the function's gradient is when x is equal to 1. All right, let's do it. 2 times 1 is 2, take away 1, which is 1. Okay, therefore, gradient of tangent is 1 when x equals 1. That's what it's basically saying, is the gradient of that line is 1 when x is equal to 1. Right, that's a bit of a fluke on my part using GeoGebra there. I didn't know that that would come out as 1, but that was just a rough guess. But yeah, you can see how you can quickly determine or have a good look if you have a graph with you.